Hi, I'm Eric Hogersten. I'm going to speed date you for the next 10 minutes. Company called Acumem. I used to be a Sun employee many years ago, building large-scale servers. This is about performance bottlenecks. So there's lots of excitement and lots of promising stuff happening with multicores. Two things that may be less exciting are these two bottlenecks I'm showing here. Since a larger fraction of the chip area is devoted to CPUs or cores, a smaller chip area is devoted to caches. Duh. And furthermore, that smaller area devoted to cache is not going to be shared by many threads. Okay, so the cache capacity per thread is not going to be as large as if we were designing CPUs the good old way we did way back. Furthermore, the bandwidth is going to be a limitation because all these threads are going to miss more often in their caches and more often will have to go to the memory. And we already see a problem with memory bandwidth in many applications. This is likely to get worse over time. So if you look at the prediction in the future, with the speed of transistors and the number of transistors you will be able to put on a chip, the compute power you will be able to put on a chip with increasing number of cores, and you see how that matches the prediction of the pin bandwidth of chips in the future, according to the Silicon Industry Association. That's a pretty sad picture. It's bad today, but they predict that in the next 5 years or so, it's going to be worse, a factor of 5. So what are we going to do about this? Are we just going to keep building multicores, or are we going to be able to master these two new bottlenecks in any way? Well, this is what the picture looks like today. I'm taking one application from the spec benchmark suite, just representing an HPC application here, LBM. If you run that on one core, the CPI of that process is already fairly bad. It's maybe like 2.0 or something like that. But let's normalize our throughput to 1 for that pretty poor execution. When you go to 2 cores on the same chip, the throughput increases by 50%, and then actually the throughput decreases because now all these threads or these are going to fight for those shared resources I talked about. If you think that's something that has to do with just one application, that's not completely true. This is just doing the same kind of calculation. What's the throughput improvement when you go to a quad core compared with if you were just activating a single core on a chip? And across all these applications, typically half of the applications have a throughput of 2 or lower. Of course, on a quad core, you would like to see a throughput of 4. So going back to that application again, what we can do with Acumem is, if you have such applications, we can give you hints of how to avoid those kind of bottlenecks. And this just gives you the throughput example of LBM after one of our new hired employees spent a day on that with a tool fixing some of those bottlenecks. And now it actually runs pretty much okay. So the technology that we bring to bear it's a performance analyzing software. It's completely, absolutely different from anything else you've used. We do not, I repeat, we do not collect hardware counter information that we base this tool on. Rather, when you run your completely unmodified binary on your favorite computer, we will collect a rich set of statistical data of that execution that has nothing to do with hardware counters. And we collect that data, maybe collect data about every 1 millionth access or so. And we measure some rich information about that, collect that in what we call a fingerprint file. 1 megabyte, 2 megabytes, 4 megabytes, something like that size file. That fingerprint captures how that source code and that compiler plays together and what kind of locality properties you are getting in your application. Of course, no human can understand that fingerprint file, so we use an analyzer software to analyze what's going on. And that analyzer software will present some very exciting graphs showing you what really is going on in your application. And that analyzer software, you can tell that analyzer software what kind of system you really would like to run the code on. So you can give architecture parameters which are different from the system on which you capture the fingerprint. The fingerprint is architecturally independent, and at the time of the analysis, you tell me, I would like to run on the next generation system. Now tell me, will there be any bottlenecks there? Also, what you get from the analysis is what you call the virtual performance expert. This used to be known before as the virtual RUD, but we renamed it to virtual performance expert. Does the same ad as RUD would do to an application. It really finds all the spots where there's a chance of improvement, but it communicates this in straight straight message to the programmer saying, putting the finger on exactly where, what the potential is, how much better can you run this application, tells you what the different issues are, allocation of the data structure may be done in an unoptimal way, loop order may be wrong, tells you exactly where in the code you should apply these changes that we suggest, and we give you lots of how-to information as well. So if you're not a skilled programmer, if you're not rude, well, maybe you have to click on that link and we will take you down and give you more information about how to go about this. So just a quick example. This is a overall picture that you may see of an application from this analyzer software. This gives you, at the top graph, tells you the miss rate of this application as a function of cache size. You get that from a single fingerprint. A programmer has probably never seen this graph before. So it tells you, how much you're missing, and also tells you the footprint of this application. Is this footprint, is it close to fit in my cache of 1 megabyte? Probably not. Okay, so we can't do kind of squeezing that way. We have to get the miss rate down from the top and down. That's an interesting curve for a programmer. What's even more interesting is the blue curve, which shows you the utilization of this program. So utilization tells you that how large fraction of the data brought into the cache is actually used by the program. And this may be shocking to you, but most often the data in the cache is not used by the program at all. It's just dragged into the cache, never used, and that's thrown out again. We also give you tells you prediction of what would happen if you fix the utilization because you want it to be 100%, right? So if you do these fixes, the advice from the tool, I'm not going to go through this in detail. We give you detailed advice. These are the 3 places in the program you need to change. This is how you need to change it. And if you change it, well, the prediction came true. The miss rate went from 4% to 2% in this application. The scale is different on the 2 graphs here, just as we predicted. Throughput of this application went up. So throughput, which used to be very bleak, is now almost up at 3 for this application. And this is after new hire spent 30 minutes on this application. So this is what the tool looks like. You get this curve, as I showed you before, as your first view. Lots of summary stuff. You have tabs up there in the top. You can tell me whatever you would like to do next. So you can, for example, get a loop-centric view. Tell me about all the bad loops. Or you can click on the bandwidth issue. Tell me all the issues that hurts my performance because the CPU is waiting for memory. Or you can have bandwidth and latency issues, which is the CPU is waiting for memory. So let's click on the latency issue. What you get from this tool are the 3 top bad examples in the code. You click on one of them. On the left-hand corner, you get an ample of information about that issue you clicked on. You can get all those nerd curves and all that stuff per instruction. You can get that information per loop. You identify the place in the code that's bad. And you can drill down, get more and more information. And this is presented at a level that a normal programmer would be able to appreciate this and actually go in and make the fix. So that's latency issues. But what's even more important are bandwidth issues. So the bandwidth it's not just that the cache misses that eats bandwidth. Actually, more often the hardware prefetcher is the beast that eats the bandwidth. But if you just look at cache misses, you wouldn't see that. So let's click on the bandwidth issues, and you will see a much richer list of things you need to fix in the code. Of course, you need to fix that as well if you would like to avoid the bottleneck. That's all I have time to show you right now. Killer apps. Do you have a killer app? What is a killer app? A killer app is an application that uses the bandwidth and the caches in a wasteful way. It ruins the life for itself and for others. It ruins its own scalability as well as the performance of other applications that may be co-scheduled on the same core. Throughput potential has no throughput potential. Parallelizing is not going to help because it's already limited by its resources. You've got to find the problems, you've got to fix them. So at supercomputing, we have a demo station in the Sun booth. We have our own booth 269. I'm going to be presenting the return of the killer applications there with a little more data. Each day at 11 minutes past 11. I thought it was a good time because you are nerds and that's a binary number, so you can remember that. We have a presentation at the vendor forum Wednesday at 2, and we also have a presentation in the Sun Theater also at Wednesday at 5 o'clock. We are supporting x86 Linux as well as Solaris x86, this tool. We have promotional pricing. What we feel is a quite low pricing. We want people to test these out. $750 for industrial customers and $350 for academic customers right now during November. Our website is coming live on Monday, so you wouldn't be able to find that information just yet on the website. Thank you so much.
Thank you so much, Eric. Any questions for Eric while we prepare for the next presenter?
We do not have a Spark version just yet. We're looking into what different kind of architectures and operating systems to support in the future. So I'm happy to take your vote on what we should do next. It does support self-modifying code, but Java is sort of a problem if you want us to point down in the application what's going on. That's sort of one abstraction level away. So right now you wouldn't get meaningful information down in Java.